Okay, today we will start a completely new topic. Some parts of this topic issues have been covered before, so we are already aware of some of them, but some other things are more related to some new concepts. And those new concepts are very popular image processing concepts that many people are aware of. As a matter of fact, most of the image processing based books and literature are related to the final things that I will be mentioning about for today. And they are basic pixel operators. The basic pixel operators is it's a wide topic. We will only cover a few of things. And we will start with one thing that we have already started seeing, and those are the gradient-based operators. And the gradient-based operators are, as we know, trying to estimate the gradient of a two-dimensional surface for typically for image processing, for edge detection purposes, because we know that if there's an edge on the profile of the image, then along some certain direction, we have a gradient, a large gradient that actually corresponds to a pixel intensity change, an abrupt pixel intensity change. And we will be talking about, like two gradients, vertical and horizontal. Let's say that G1 is the horizontal gradient that is performed by a horizontal gradient operator acting on X. X is the image here, and H is the horizontal gradient operator, which is kind of a derivative filter. But of course, those derivative filters have only some estimations in finite discrete time, and G2 is the vertical filter. They are high-pass filters because we know that the derivative filter is a high-pass filter too. And in continuous time, the derivative filter is just j omega, as we know. And j omega is equal to 0 at omega is equal to 0, so it doesn't pass the DC. And as omega increases, as the frequency increases, j omega also increases in magnitude. Therefore, it's having a high frequency emphasizing attitude. The gradient from these two directional high-pass filters or their estimates are then usually obtained by extracting a scalar from these two gradient magnitudes, like this or like this in magnitudes, because we don't care whether it's an uprise from a low intensity to a high intensity or from a high to a low. We don't care about that. That's why we're taking the squares or the magnitudes of those things. They both correspond to an edge. Now I want to mention a little bit more about the pixel-based operator aspect of this gradient concept that we have previously seen, which is what could be, for instance, an example of H1. An example of H1 is this. It's a 3x3 convolutional template, also known as the Sobel operator, right? And it's probably one of the most popularly used ones. The Sobel operator is also used for another very popular operator for edge detection, also known as the Kenny edge detector. But Kenny edge detection is a sophisticated extension of this one, which is doing some further analysis after the gradient. So you have the gradient, so what? They don't really correspond to the edges. How do we find the edges? There's a thresholding, of course, necessary above some threshold, it will correspond to an edge. And edges must be contiguous, so they must continue along a curve because they are usually boundaries of physical objects on a picture. Therefore, we don't really need, for instance, edges if there is noise, because noise will have a lot of edges, right? Just lots of intensity changes, but those edges will not really produce a continuous line or curve, a smooth curve. They will be just wrinkles, local, abrupt changes. So filtering out those things and deciding whether it's an edge or not is a further process that is typically applied in canny edge detection. And I really recommend that an image processing knowing person should be aware of how canny edge detector at least works and what kind of things it considers. For example, it considers the length of the edge line segment or curve segment. How long is it? It must be sufficiently long to be considered as a pronounced edge. But this is the gradient operator now we focus to, which is the Sobel operator, known as the Sobel operator. Now, it has two structures to be considered. One of them is the way that it's running along the horizontal axis like this. And along the horizontal axis, we see scaled versions of -1, 0, 1, which is a high-pass filter. It does not pass the DC because the sum of the filter coefficients is 0. Therefore, the DC does not pass. And from a negative to a positive, or from the positive to a negative, if something is happening, it also detects. But it's not -1, 1, for example, which is also a first gradient or first derivative approximation. But this one is particularly useful for local salt and pepper type noises or local line segments. Suppose that a line is being or passing from this yellow, if you can notice from the screen, I have marked the 0 as a vertically yellow thing. Suppose that that yellow thing corresponds to a 1 pixel wide line in the image. Now that line is not an edge, it's a line, okay? Or suppose that there is an impurity of a certain pixel. We don't really want to detect that one, and it passes through the center. If it is passing through the center and its right-hand side and left-hand side are at same intensities, then this operator does not detect that one, for instance. Anyway, so but nevertheless, it's more or less the same. And from a negative to a positive, within a magnitude, it will detect the edges, certainly. But something else is happening. If you think of it vertically, because in the vertical direction, the coefficients are, except the 0, 0, 0, okay, forget about that one. It's like scaled versions of 1, 2, 1. So this is a high-pass filter. Oops. High-pass filter. Whereas 1, 2, 1 is typically a low-pass filter. It's a smooth shape. So if you apply this operator while applying a gradient operator, a high-pass filter along the horizontal direction, vertically it's applying a low-pass filter, which is a good thing, because it's like taking the averages of the 3 pixels within the neighborhood. So it's not really only considering the horizontal and the horizontal left and right pixels like this one that we have, but it's actually taking an average of these further up and down rows, which is like making or taking a low pass filter effect in a vertical direction. And low-pass filtering is a necessary stage for before the gradient operators, because of this noise business. If there is some speckled noises and here and there and everywhere, then they will adversely affect the performance of gradient to edge conversion. The gradients will be there, of course, but they will not correspond to edges if there is granular or some noise in the image. So we have to apply a low-pass filter of some sort. And this operator, or these N by N operators, are typically applying a low-pass filter in the corresponding vertical direction of the direction that you have. So if you are finding a horizontal gradient, it's applying a vertical low-pass filter. The other gradient, this is for G1, of course. The other gradient for G2 is, of course, H1 transpose, which is -1, -2, -1, 0, 0, 0, 1, 2, 1. This one finds vertical gradients corresponding to horizontal edges. And meanwhile, it's also filtering, applying a low-pass filter along the horizontal direction. Clearly, you can see that these have some higher gains as opposed to unity gain gradient filters, low pass or high pass or whatever. Because if you take a look at this filter, for example, this 1-to-1 filter, its coefficients are 1, 2, and 1, which sum up to 4. So it's an amplification. It's applying an amplification. Therefore, it's wise, it's clever to divide those things to normalize for the unit gains. Okay, we don't really just apply it as it is if it is a filter. But if it is for gradient selection, division of this by a normalization factor, or this by a normalization factor, is no different than applying these operators directly and adjusting the edge detecting thresholds. Okay, just multiply the threshold by capital N and it will correspond to the same thing. These are not image filters, they are just operators for the detection of gradients. This is the Sobel operator of as an example. Another alternative is the isotropic filter, which is very much similar, but it's not 2, instead it is square root of 2. So the central magnitude for the low pass filtering is just slightly changing, but the gradient detection strength of these two H1 variants are exactly the same. And there are other operators where, of course, H1 transpose is used for the other direction. An interesting alternative is to have H1, something like this. And let us see if you can understand what this one is doing. Oh, sorry, it's not 1, it is 0, -1, -1. Can you notice what this is doing? What kind of an H1 filter it is? I'm expecting some feedback from you guys at this point. Is this a gradient filter, first of all? And if it is a gradient filter, why doesn't it look like the ones above? And yeah, can you elaborate on this? I'm looking for a brave heart to open up the mic and tell me what this is, how this one may also work. And what is the other gradient operator? Is it the transpose of it? Clearly, it's not, because the transpose of H1 is equal to H1. So the two gradient operators of H1 and H2 will be different. But for the previous cases, they were just H2 was equal to H1 transpose only. So what is this gradient operator? What do you see when you look at it? So no brave hearts in this class. You are already a brave heart to attend the course. The others are not even doing that one. And but you're not answering questions, you're not addressing the concerns, which is a bad thing, because I haven't evaluated your examinations yet, and I will evaluate accordingly, according to your efforts, overall efforts, and things like that. So, are you still not answering my question? What kind of a gradient operator could this be? By the way, I will also, just as a hint, give you the other gradient operator. It's this one. How come it works? Can't you see? Just observe these two operators. Can't you see that they are indeed gradient operators? Obviously not. So let me at least indicate it. They are not horizontal or vertical, but they are diagonal. One of them is a gradient operator along this direction, and the other gradient operator along this. And they are orthogonal to one another. One of them is 135 degrees, the other one is 45 degrees, and the difference between those two angles is 90 degrees, therefore they are orthogonal. They don't have to be horizontal and gradients for the detection of the edge. If most of the edges are just diagonal, then these may better work actually. As you see diagonally, there is a transition from -1 to 1 in the diagonal direction, like -1, 0, 1, or -1 to 1 in 135 degrees. The other 45 degrees ones are also changing along that direction from -1 to 1. Okay, these are also gradient operators. Now, an alternative of these gradient operators for the edge detection business is called Laplace operators. And the Laplace operators are second derivatives, and they work like this. Suppose that you have a profile like this, and that profile is a cut or a slice of your image. From a low intensity to a high intensity, there's a change. So there seems to be an edge in between in this image. When you take the derivative of this, so this is f of x, let's say. When you take the derivative of this, it will look like this. Okay? This is f prime of x, the first derivative. And usually, as you see, for the detection of the edge, it requires a thresholding or something like that. The top examples were such operators, gradient operators. But the Laplace operator, the Laplacian, is the second derivative. It's also used in physics, which is the derivative of f prime of x, further derivative. And it works like this. This is the second derivative. And in the second derivative, how can we find the edge? Then the edge is essentially at the point which makes a zero crossing. Here, this one. This is the zero crossing point. And we tag it to be a candidate of an edge. All right. This is called the Laplacian operator. and the zeros of a Laplacian operator are edge candidates. Unfortunately, the second derivative of flat regions like this are also all zeros. So if you just say that small values for the second derivative, let me mark them as indicators of edges, you will see that most of the smooth places of the image will also be completely tagged as an edge. So you have to get rid of those things by further post-processing. That post-processing is, it will be a necessary tool that you have to apply, unfortunately, for this. But such post-processing is necessary for gradient-based methods too. So this is the Laplace operator. If you watch videos or if you take a look at some illustrations from the web, search for the Laplace edge detector or Sobel operator, Kenny edge detector, etc. You will get to the details of these things. That will be available to you. The Laplace operators, or the candidates of the Laplace operators, let me briefly mention about those things. They are single operators that we don't have directions or anything like that. The second order are isotropic, rotational symmetric operators for the second derivative, and they are like this. One candidate is this, for example. And the idea that we see here is that it sums up to zero, first of all, because it's a derivative operator. Besides, it's further a second derivative operator. And such operators, negative to negative, is corresponding to the second derivative. From negative to positive will correspond to the first derivative, which is the gradient. Negative, positive, negative is the second derivative. Okay, that's an idea that you can understand. And if you rotate it by 90 degrees, you will still come up with the same. Another alternative of a Laplace operator in a small discrete time is -1, -1, -1, -1, 8, -1, -1, -1, -1. The top one is like corresponding to the for connectedness. The vertical and horizontally neighboring pixels are only considered. The second one that I have chosen is corresponding to the 8 connectedness, where the diagonal neighboring changes are also considered. And as you see, the sum of all the values of this operator is also 0. An interesting alternative is 1, -2, 1, -2, 4, -2, and 1, -2, 1. This thing also adds up to 0, by the way, as you may notice. The negatives sum up to 8 and positives sum up to 8, so they cancel one another. But vertically and horizontally, positive, negative, positive, or negative, positive, negatives appear at all 3 rows and columns. Therefore, it's a different attempt to mimic the behavior of a second derivative, which is very difficult to mimic in such a short discrete time filter of size of length only 3 by 3. Okay. Now, these are the first and second gradients that may contribute to the basic pixel operations. Now I will talk about another thing, which will be our transition point from linear pixel operators like these convolutional operators or templates to some non-linear operators. The first non-linear operator that I want to talk about is the median filter. it can be studied under the topic of morphological operators, and we will also see morphological operators. But since it's so popular for some specific types of purposes, I would like to mention about it separately. Then I will mention about it under the morphological operator business as well. The median filter or any kind of a morphological filter defines first a region of support, which is like a convolutional template. Let's assume that it is a 3x3 template that we are sliding over the image. It will be named as the structuring element where we apply the morphological operator, and the morphological operator is the median filter. It's wise to choose a structuring element which is as circularly symmetric as possible for such general filtering operations, morphological filtering operations, and the total size, the pixel count of the structuring element should better be an odd number, particularly for median filters. The reason is, suppose that we have an example image like this, which is a binary image, by the way. It's consisting of zeros and ones. We will make a stack ordering like the stack order filters that we have seen previously for another purpose. So when we apply a stack ordering of this, from maximum value to the minimum value, it will give us 1, 1, 1, 1, 1, and 0, 0, 0, 0, total of 9 elements. The median value of these 9 elements will correspond to a unique value, which is 1. And the filter output will just replace the center of this structuring element, which was this, with the median value, which is again 1. So what are we going to do with this? If the situation is like this, at least it shows me one thing. This median filter, unlike other averaging filters, mean filters, which will just sum up all these zeros and ones and divide by 9, it would give me a blurry value. It will blur out the edges, whereas this median filter will give me one value from the image itself. So it keeps the edges. Or it keeps the sharpness of the edges. And that's a nice property. That's one nice property. However, it also has further nice properties, as we have previously indicated in other lectures. Like if the situation is like the values are 99, 101, 105, 102, and the structuring element's center position is 12, and the others are 95 and 100 and 99 again and 103. So it seems to be like the pixel intensity within this region is quite gray, with an intensity value around 100. But there seems to be one problem, which is this. A pixel with a value of 12, which is exceptionally dark. Such a thing will be called a pepper noise. Of course, if it is way brighter than the average region, it will be called a salt noise. So it's a salt and pepper type of noise. Salt and pepper noise, which is just black, totally black or totally white, and isolated, just a few pixels, like 1 pixel for this example. If you make a stack ordering of these, the highest is 105, and then I have 103, then 102, 101. There is 100, then there is 99, there is another 99, there is a 95, and then there is 12. Okay. So if you apply the median filter, it will pick this 100, and it will replace this 100 with the value that was previously there, that is 12. So the median filtering eliminates such impulsive noises. Okay, simple fact. That elimination is a good property, because if you use a linear filter, a linear blurring filter, it will blur out or average out all these values that we have, and it will be less than the average. Because of that 12 over there, it will start to adversely affect the overall intensity, and the whole thing will just be a little bit darker. This one does not really make that kind of a blurring. Therefore, it doesn't affect the edges. The edges are kept, and it eliminates or isolates or eliminates isolated salt and pepper types of noises. Now, the one thing that we can notice is that it's not only for 1 pixel salt and pepper noises. If the salt or the pepper within this structuring element is smaller than, for this example, smaller than or equal to 4 pixels, so it could be maybe like this. And let's say that these 4 pixels are outliers. They are too large, like a salt, a white speckle, or a dark speckle. But up to 4, the median filter will still work, because as you see, the count of these is 5. So 5 pixels from the natural scene and 4 pixels from the outlier. If the natural ones are larger in value, for example, they will appear at the top, those 5, and then 4 outliers will be at the bottom, and the median will be from the natural pixels. If they are smaller than the red outliers, if it's a salt noise, in other words, then the situation will be flipped, and the first 4 will be too bright, and then the last 5 will be the normal scene. One of them will be selected, one of the pixels from the normal scene will be selected as the median. So it still works. And it's a very common practice to ask, what is the condition of the size of the speckle that you have if you have a certain structuring element size? Or conversely, if your largest noise, salt and peppers, are consisting of some certain number of pixels, what is the size of the structuring element that you must apply, right? And they are simple relations. Now, what are the other morphological operators? Let's continue with that. These morphological operators are nonlinear operators. There are 3 types of image operators that we can think of, or there are 3 ways to interpret an image. The first interpretation is the intensity image, where we usually look at, we usually apply linear filters, but that's not necessary. Nonlinear filters can also be applied to intensity images. And humans, the first step in the human visual model is is acquisition of the intensity map using the camera that are our eyes. The second way of looking at the image, there are, I said, 3 perspectives of looking at it. The second one is more related to the brain interpretation, which is the shape information. Shapes. For example, for black and white images, black may be the background and white may be the foreground. So the foreground will correspond to a shape. Is it circular? Is it a star shape? Finding the edges, edge detection, and making thresholdings for detection of the edges, etc. They are towards a more brain-wise interpretation of the image. So morphological operators are usually related to those shapes. They are shape operators. They are not really intensity operators, but they will act on the intensity maps, of course, but they change the shapes. And morphology is, by the way, from Latin, corresponds to shape science, science of shapes. Okay. So intensity, shapes. What's the third one? The third one is the topology, which is the science of surface. So the three-dimensional surface, which could also be considered as an intensity if you look at the higher surface points will correspond to brighter pixels and lower surface points will correspond to darker pixels. They will be transformed into intensity, of course. It's not morphology, it's a different thing. It's called topology. And flooding the topological maps to apply thresholding, etc., they will be called topological operators. Within this course, we will not be dealing with the topology or the topological operators that are also a part of image processing, but we will briefly talk about morphological operators. And the first morphological operator that we will talk about is erosion. This is the first morphological operator. And erosion, the name is English. It comes from Latin, and it's like losing some part it corresponds to. If you erode a shape, it means that preferably from the boundaries, some parts of the object are lost and the object becomes smaller. Erosion is also used in, for instance, geography and in agriculture and things like that, where rain, for example, chips off some parts of the soil that you have and it just throws it to the sea. That's also known as the erosion. So at the end of erosion, the size of the object becomes smaller. And the shape of the operator that we will use, or the notation that we will use, will be this. A circle with a minus sign in between. So that is the erosion operator. X here corresponds to the image. This is the operator. And this B is the mask, or yeah, it's the mask, also known as the structuring elements. So erosion depends on how you erode. So B is important here. It's like your knife, where you chip off some parts of from the object. If the knife is too big, you will chop a lot, and if it's small, then you will slowly peel the edges of the image and of the shape, and it will become slightly smaller. So B is something here. It's a thing. And the definition of this in binary images, I will also mention about the gray level image definition of an erosion. It's this. The set of all pixels X where the mask is totally including the image, or included in the image, excuse me. The mask is totally included in the image. These kinds of notations are usually hard to understand at first, but when we understand what or how they work, we try to make sense of those mathematical notations. I'm not a huge fan of these mathematical notations, by the way. but for literature writing purposes, they help. It helps transferring the information from one side to another side. Suppose that the image X is consisting of these pixels. Like this, okay? It's a very small one. The dotted portions correspond to the object pixels, like ones, let's say. And anything that I do not draw is a background, or I do not indicate as a dot will be the background, which is, let's say, 0. Then the mask B here, let's say, is like this. So it consists of 3 points, 3 active points. So the erosion of X using B will look like this. We put these 3 pixels inside X, or within the image that contains the object of X, and slide it over X. If B is completely contained inside X, then it will correspond to one object pixel. For example, here I can see that if I choose these 3 red pixels, it will mark one output. So let me indicate it like this. So these 3 pixels will mark one output at X eroded by B. Then I will choose, slide it to the right, which will make this green, and this green pixel. They are still inside the image, and it will make another point, which is to the right, because I have slided the template to the right, so its output is 1 pixel to the right. When I shift one more to the right, it will still be inside X. B still, it will still be inside X. But if I further go to the right, it will not be inside. Okay. 2 of them, like this, will be touching, but one of the pixels of this blue one will be out of the X image, so it will not be completely contained. So this is not a valid output. So we end. Then we go down by one row and then make the slide again. It will go on like this, like this, like this. And it will go one more, because this time these blues will be like here, here, and here. As you see, on that corner position, everything is included. So I have one more. But if I go one more to the right-hand side, one tail of this 3-point operator will be out. So I go down one more time, and then it will have this 2, 3, 4, 5, 4, and 5. Yeah, it will have just all of these things, 5 points. But the 6th one will be out. If I go down one more time, it will be out. Some parts of the B will be out of the X shape. If I go to the left more, to the right more, or to the top more, some portions will be left outside. So the eroded signal will be this. Just compare it to the original X. As you see that it's smaller a little bit from all sides. So it makes it smaller. This B, by the way, is a bad one. It's not, I cannot say it's a bad one, but for general shrinking purposes, it's not symmetric. It's just L shape. So why don't we just use a square shape, 4 pixels, 2 by 2? Well, But this is an example anyway. And this is what the operator tells us to do. This is called the erosion. And it's a morphological operation like the median filter, because it could also be notated in grayscale as, not only grayscale, for binary too, as this, the minimum of B around the pixel position of X, like the B sub X of the top, intersection the shape image, the minimum of it. So you intersect the L shape and X, their intersection will consist of some ones and zeros, and you're choosing the minimum. If there is a zero, which means some portion of B and X are out of each other, so their intersection will contain some zeros. Whenever some zero is contained, their minimum will be automatically zero, so it will produce zero output. If they totally intersect, then their intersection will only consist of 1, 1, 1, 1. And their minimum will be still 1, which will be an on flag for X erosion B. So this is also an accurate definition of erosion. And it also works for grayscale images. BX is still a shape, it's a mask, but X could have values between 0 and 255, for example, or anything between 0 and 1, real values. Within that mask, the minimum of X pixel values will be the output. So if you erode a grayscale image, since you are choosing only the minimums, the intensity of the image will be smaller. It will be lower. It will be a darker image, in other words. The median picks the center value, therefore the intensity does not really change. If you average those pixels, the overall intensity will not change. If you pick the center, the overall intensity will not change. But if you persistently choose the minimum one, the intensity will be significantly lower, of course. It's producing a darker image for grayscale. So this is what erosion is. And the opposite of erosion, before the break, this is the last thing that I will mention about. After that, we will give about half an hour of break. We can meet at 11 o'clock and we will do the last lecture. The opposite of erosion is the dilation. The first time that I heard of the term dilation was in medical science, actually. It's a biological thing, where the dilation of the human eye aperture, which is called as the pupil function, okay? If it dilates when it's dark, because it automatically behaves like that biologically, if you're alive, of course. But if you're dead, it does not dilate, or it does not contract when you turn on the flashlight to the eye. It should contract. It's the opposite of contraction, actually. Dilation is expansion. So it's a test for whether the person is dead or alive. That's an interesting test, isn't it? So they put a flash on the light on the eyes, and if it contracts, and when you remove it, if it dilates, then the person is essentially living, it means. So dilation is expansion in shape. So that's the opposite of erosion. And the notation for that is this. Okay. They look like logical X or X and operators that we are more familiar with from digital systems, but this is not that. It's just the notation that we use for dilation here. And its black and white definition is the coordinates of all X where the mask around the position of X intersection with the shape is non-empty. Previously, it was Bx must totally be intersecting X. So Bx must be totally inside X. But now I'm telling you that their intersection must be non-empty. So as long as the mask touches the shape, the output still flags an output 1. So for instance, if you have this image, okay, and you again have this, so this is X, this is B. How do we dilate X with B? We slide to the top left corner, which may be somewhere here, for example. We can start from that position, top left corner, a little bit above beyond the top left corner actually, but the L shape, L edge touches to the shape. Therefore, the output will flag an output 1. When you slide it to the right, they still touch. It's a 1. When you slide it to the right, it still touches. So it's a 1. When you slide further to the right, it still touches. It will be like this. As you see, it touches. I'm sliding that L shape. And some parts of this L shape pixels are touching to the X. When I go down by 1, it will touch, 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 and touch again. When I go down one more time, it will touch, 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 and touch once more, like this. You have to be careful about doing this, and you have to make sure that you can come up with the same result. You have to be careful. If you go down again, this position does not actually touch, because the L shape will be like this. So no pixel of that L shape is touching the black pixels. So we don't have this position. But to the right of it, it touches. To the right, it touches. To the right, it touches. And to the right, it touches. And it becomes, and then nothing more touches, of course. It becomes like this. Originally, it was like this. So from this to this, it's a dilated image. As you see, shape-wise, it's becoming wider. There are more pixels than the previous one. And finally, in gray level, so this is the binary definition. In gray level, it makes even more sense, because the new definition is just the maximum of the max around X intersection X. So inside the mask, you pick the maximum value. So dilation is a maximum filter. You stack order and pick the maximum. Median is a median filter. You stack order and pick the middle value. And erosion is the minimum filter. You stack order and pick the minimum. Okay, so maybe I should write it like this. One more. Okay, this is the median filter. This is dilation, and this is erosion. The minimum is the erosion, the max is the dilation. Okay, these are the erosion and dilation, very popular and very well-known techniques, so you should be aware of these things. All right, now I can stop. We will meet at 11 o'clock. We will continue with the rest of the morphological operators till the end of the course. And then, as I said, next week we don't have a class. It's a pass week. And the week after that, it's your turn to make presentations and submit your projects. So now I'm stopping.